Hey everybody, welcome to Skyter Livestream. I'm Mark D'Antonio, the one and the only. Well, according to Facebook, there's 58 other Mark D'Antonios out there, and I'm the 58th now. My profile is still not back on Facebook, but people are reporting that they're seeing my black and white image from my old profile now and then. So it's out there. We just haven't figured out how to get it back yet, but that's okay. Anyway, I wanted to say hello to everybody and welcome you to Skyter Livestream for this wonderful October 2nd. October, oh my gosh. And Daryl is with us. Hey there, Daryl. How's it going?
Hello, Mark. I'm well. How are you doing? Hello, everybody.
Oh, just fine. I'm just interested to find out how things are going out there in Colorado, where you are.
It is starting to cool off.
Okay.
Had a couple of thunderstorms pass through here earlier tonight, and supposed to be quite cool by Wednesday.
Wow.
October 15th, 1984, it snowed 3 feet here in town.
Holy cow.
4 feet just south of town.
Wow.
So, that was unusual, but you never can tell here.
Mm-hmm. Wow. Well, here the temperature was...
Knock on wood.
Or Formica, as the case may be.
Yeah.
The temperature here today in Connecticut was around between 68 and 72. Very pleasant. Didn't need a sweatshirt. So it was very nice. And so I figured, look, I've been waiting for a stream. The moon is not risen yet. It's past full, so we've got probably an hour or so before the moon comes up. But we'll hang in there and try some stuff to see what we can get. It's on the backside, so it's getting smaller and smaller. It's waning, Very cool. So this right here that we're seeing, this is called the Omega Nebula. And the Omega Nebula is located over here. This is the Omega Nebula. If I back out, you'll see where it is. Okay? And it's actually a beautiful nebula that, we think has stopped doing stellar production because it doesn't seem like it's been doing a lot of it. It's in Sagittarius. Okay? It's also called the Swan Nebula or the Horseshoe Nebula or the Checkmark Nebula or the Lobster Nebula. I don't know why. Daryl says it's the Duck Decoy or the Duck Nebula because it kind of looks like a duck. If we flip this upside down, there's the head of the duck, and there's the body, and there's the little feet paddling like mad.
Most people see a swan there, so I should call it the Swan Nebula.
I grew up with it as the Swan Nebula when I was 9. That's how I learned about it, was as the Swan Nebula.
Yeah.
So that's pretty interesting.
Old-time astronomers supposedly saw the Greek letter omega in there.
Yeah.
I suppose it's lowercase omega. Or a check mark. Or
yeah, this could be construed as the capital Omega, this section right here, I guess. It depends on how you look at it. I have no idea. But you'll notice something, guys, and that is that in this image, we're at 27%. If we zoom out a little bit more, you'll see there's more nebula around here. Okay, there's a lot of stuff in here. There's a lot in here that, in fact, if we can, over there in the corner there, we can punch up over here, we can punch up the processing just momentarily to show you what else is really there. Look at all that. That's all back there in the background. And you'll say, why don't I keep it there? Because I want to maintain these details here in the center. If we want those details in the center, we got to do it this way. So that's okay. And we can just kick this out a little bit and pump this up. This is the mid-level, and that yellow bar is intersecting more of the light curves. These are the curves coming in from the camera. You have red, green, and blue, RGB. And this yellow line represents the data we're pulling in. If you can see this area under this curve, this right here, all this stuff in here below the yellow curve, that's the data we're pulling in. If I move this line to the left more, you'll notice it intersects more of the data, and thus it gets brighter and brighter and brighter. Now look at that. There's a lot going on here. And if I move this over a little to the right, the dark level, you can move it to just to the left of the peak of the curves, and that's where you'll get your data and not lose any data. Move it to the right of that curve, and look, you start losing data. Okay, but stay to the left of the curve, all right, and you'll be ahead of the curve, and no pun intended, and you get all this additional data. It's just stunning. So a happy balance is to be able to show the inside of the nebula, and there we are right there. Okay, and go a little more, and you can even drop it down. And if we go even further, then we can dig into the depths of this nebula even more. And that's the beauty of the cameras we're using. This is our new camera, and look at that. We can now see all this modeled data in here, and if we can zoom in now, look at that. That is incredible.
That's very nice.
Look at all the detail in there. Detail that has been elusive to us in the past, but tonight, now it's there. And I will add a little bit of a sharpening process to this, and that will kind of make that look bright, but you also get a little bit more of the wispiness inside this structure. You can see this dark cloud that's obscuring what's behind it. There's a lot of dark clouds in here. All right.
There's some really nice detail over there on the far left, too.
Oh, I know, right over here.
Loops and whirls and stuff.
Yeah. Now, those loops and whirls, by the way, guys, those loops and whirls come from a variety of processes in the interstellar medium, not the least of which is past supernovae and new stars that have pushed gas with their stellar winds and ionized it, and therefore made these arcs. And so it looks like a free-for-all out there, doesn't it? But look at this little subtle piece right here now. Look at that little guy right there. What a gorgeous little wisp that is. Again, we've never seen that before. This new camera, it's just amazing. It shows us the most incredible stuff. I am very impressed. You know, and after visiting out there to fix the alignment problems, I think we're looking good too. Now, this is also known as Measure 17, and it's, you know, colloquially known as M17. So that's this guy right here. Okay, and we put it right up there so you can see it. All right, I can actually move that maybe up here. Keep it out of the way.
Mr. Django would like to know what model is the new camera.
Sure, it's the ZWO 183 MC Pro. So it's a color one-shot camera, and we get our RGB curves, as you can see right there. All right, that's these curves here, and if I move it over, you can see better what it really is doing. Let me just do that. So let me move that over, just push that a little further along. There you go. So now you can see the data, and these lines represent how are cut into the data. Here's all the data, and if we put all this data in here, okay, then we have way too much data. So watch, I'll put it all in here, okay, and now look at, now we got lots and lots of data, lots of nebula in there, but we also have an overblown saturated center, which is not what we want. All right, so if we take it all the way to the bottom of the curve here, and come along down to here, if I just go like this and grab most of the data, so now we're in this region here and we're carrying all this data. You can see that's still too bright. So what we do is we adjust for a happy medium, all right, which is just before the beginning of the white curve. The white curve is the average of the three. So I can actually do a color correction right now, and it will tighten up our curves. You saw they now are all more and less aligned. And then we can drop down the central brightness, and that'll actually afford us the ability to see more detail in this part of the nebula. I'm seeing globules in here now, Daryl. Look at, there's one right here we've never seen. There's one right there. There's one right here, very clear, with even a red ionized edge to it. There's a lot going on in here. Now, for those who want to know the best way to view what we do, most people will put this up on their big screens, make some popcorn, and sit in front of the TV show that this is. This is effectively like an astronomy program, live. And this is live. You're seeing this live. This is the universe live in real time, which is our phrase that we like to use a lot, because it's exactly what it is. And
I see a bikini top up the top right.
Here?
Sure.
Oh yeah, I guess so. One side and the other side. Yeah,
That's putting it nicely.
that's true. And we keep it G-rated because we are G-rated here. So I just want to say hello to folks that are here. Renee Cruz was the first one here. Hi, Renee. Michael Hedrick was next. Yay! Good to see you too. Tim F. Woohoo! All right, he's here with us. We have Renee Barron's with us. I saw her. There she is, Renee. There she is. How you doing, Renee? And we also have look at Daisy and Zoe. There's Daisy and Zoe Amethyst. They are always very welcome here. Rockstar is with us. Mr. Django, who I believe you're in Belgium, aren't you? And I'm wondering what the weather's like over there. Asher is with us. Asher Rial, how you doing? And then we have Alicia Vieras. Hello, Alicia. How are you, Donovan and Darlene, doing? I'm hoping that you guys are doing great. And I had the opportunity to meet them, all three of them. They're wonderful, wonderful family. Wonderful folks. Michael
Hedrick has a question.
Okay. Go for it. Was he asking you or me?
Either of us, I guess.
All right, well, read his question, and then we can...
Yes. Please tell us, is there a star category which is the same density as the Sun, but much larger in size? Density, I don't know about that.
Density might be the wrong word, yeah.
Yeah, if you're saying the same stellar classification, a G star, a G giant, I suppose. Our Sun is a Class G star. They call it a Class G dwarf, I believe. Are there Class G giants? Probably.
Yeah, there are. And see, the way Dale is explaining it is literally half the equation, and he knows this. He just hadn't gotten to it yet. But you have what's called a spectral class, and then you have a luminosity class. So, if you look in astronomy, what these classes depend on, okay, then you'll notice and see, for instance, how having a star that's G doesn't mean it's going to be about 1 million miles across like our Sun. Not always. You can have a star that's a G class star. However, it could be as Daryl said, a giant. Now, how could that be? Because it's not the rating, the OBAF GKM rating is based on temperature, all right, not on its brightness. So if it's a much bigger diameter star, it's going to be much brighter, and that is what we call luminosity. It's the intrinsic brightness of the star, okay? And so when we talk about a G-class giant, then we're talking about a star that's highly evolved. It's already used up its hydrogen and pumped it in, made helium. The helium's probably burning into carbon and fusing into carbon rather, and then oxygen and nitrogen, and possibly a few others after that. But during that time, the color of the star might be a yellowish white, so it would be called a G-class star. However, its intrinsic brightness is much, much higher than the Sun because it's expanded in size so large, and that's what we call the luminosity, and that's got a class all its own. So to get the spectral type, you have the spectral class, and you have the luminosity class, okay? All right, and that spectral class and the luminosity class together make the spectral type of the star. So our sun is a G2. Now that's a numeral 2 because within the OBAF GKM color classification, it goes from 0 to 9. So a G0 star is going to be slightly less whitish yellow and be more toward a white star, kind of like the F stars might be. All right, and so that color class, that spectral class, depends only on the temperature. All right, and the temperature and the color are intricately related. All right, and that temperature, for those that are into the science of it, that temperature is related through something called Wien's law. Okay, Wien, Wiens, Wien's law, and it represents the maximum wavelength that a star gives off for a certain temperature of the star. Okay, and that wavelength is going to translate directly to a color. All right. So when Daryl said about the stars being a giant, yes, they will be, because as they expand, they might have been very, very hot stars, but as they expand, they might cool off enough to look like the color of a G star and the temperature of a G star on its outer surface. Okay, and that means around 10,000 degrees Fahrenheit. Okay, so we're talking about a combination of that spectral class and then the brightness class, the luminosity class. So our sun, on our classification, is a G2. So it's 2 steps in from a G0. Okay, 3 if you count the 0, 1, 2. Okay, and it's a Roman numeral 5 or a V class star. So it's a G2-5. That's the entire spectral type of our star. Okay. So a star that's a G-class star, that's a big, big star, will have a different luminosity class, and there's a bunch of them. There's a Roman numeral 1, which is like an I, right, and A. Okay, there is a 2. There is a Roman numeral 3. Okay, general giants are 3, so a G3, or say a G0 Roman numeral 3 star is a G0 star that's a giant, and there's a 2, and so it's interesting how that all works.
I would assume a G giant star is evolving from something to something else, from one stellar class to a different class, and G is just along the way.
That's right.
Yeah.
That's right. That's exactly correct.
Michael had another question. Let me take a swing at this one, please.
Sure, we'll read it first, of course.
How common is it to have a moon perfectly eclipse its sun with the right distance like our moon does for us? No other moon in our solar system does, right? Yes, Michael, but it's a process. You probably heard in the past the moon was much closer to Earth than it is now. Mm-hmm. The moon's tidal effects on Earth and its oceans is slowing Earth's rate of rotation, and due to the laws of angular momentum, the total energy in the system has to remain the same. The end result is the moon is moving away from Earth over time. In the past, the moon was closer. Where we are right now, we're in a sweet place for the eclipses, that the sun and the moon on average are about the same apparent size in the sky.
Yeah.
The sun, of course, is much, much bigger, but it's much, much farther away.
400 times further than the moon. Okay, kind of a thing. But yeah, that's the right approach there.
May I continue?
Yes.
Okay. Even now, because the moon's orbit is elliptical and Earth's orbit around the sun is elliptical, they're not circular, they're elliptical, egg-shaped. The distance from Earth and moon to the sun and the distance from the moon to Earth can vary over time. Sometimes already the moon is too small, too far away, and thus too small to completely cover the sun. and that's when we get the ring of fire eclipses, the annular eclipses, like what's going to happen on October 14th here. It's going to be a Western thing mostly. It's going to drop. I mentioned this last night. On the morning, the midday of October 14th, the moon will eclipse the sun from Oregon down across the Four Corners area in the western U.S. here, cut down across New Mexico, pass into Texas, and then on down into Central and South America. The moon will be too far away to completely cover the sun at that time, so you'll see a ring of sunlight around the edge of the moon at midpoint of the eclipse, at annularity. Sometimes the moon is close and the sun is far away. You'll get a total solar eclipse at that time. And sometimes it's more so than others in that you get a long duration total eclipse. Sometimes they're so close to each other that you'll get a short or a very short duration total eclipse. And no, we're the only moon planet pair in the solar system that does this.
Although you can see Io from Jupiter eclipses from Jupiter's perspective, its shadow being cast onto Jupiter shows what an eclipse looks like from the other side. If we were at the sun side of things, looking at the Earth, we might see the moon's shadow passing in front of the Earth and passing over the Earth. And from here, we can see Io passing over the surface of Jupiter. Now, Jupiter is pretty large, so we see that little black dot crossing Jupiter's surface. So, pretty interesting.
Yeah, and it's not just Io. All four of the Galilean moons of Jupiter will cast an eclipse shadow on the face of Jupiter.
Yep. So they're relative. Now, they don't have to be exactly in the same plane as the solar system to eclipse Jupiter, because Jupiter is so big. It's like 84,000 miles in diameter or something. So it's quite large. Hello, Judy M. Hello, Genghis. Good to see you. And welcome. I was also going to say, when Daryl talked about the moon having been a lot closer, the process by which the moon drifted away has to do with angular momentum stealing, and he was kind of giving it to you there straight and certainly. But see, we have a tidal bulge. We have water, and the moon's gravity tugs on that bulge. All right, but the Earth is also rotating, so the bulge kind of leads the planet a little bit. It's not directly in line with the sun, which is pulling on it, all right, or the moon. It's kind of tilted. So the moon is actually being pulled along by that tidal bulge just a tiny fraction of an amount, all right? And that speeds it up in its orbit. And when you have an elliptical orbit or a circular orbit, you add a little speed to it, and it starts to spiral slowly away from the planet. And that spiraling away, in our planet's case, takes it about 3 centimeters every year. So it's a long way to go. Now, you might ask, well, then when would it be free of the Earth? And there will be a point where that will no longer be here on the Earth. Now, as it does that, because it's stealing momentum, that process of the gravitational bulge tugging on the moon and pulling it is also that gravitational bulge now leading the Earth is being pulled back a little bit, slowing down the Earth's rotation. Our day used to be 4 hours long, believe it or not, and the moon was a lot closer. As it spiraled slowly away, the day slowed down because of that momentum stealing that the moon is doing. So our loss is the moon's gain. And Darrell was right, saying that conservation of angular momentum is in play here. And so it's interesting how the Earth is lengthening its day and the moon is zipping away a little further each year. So,
I mean, 2 or 3 centimeters a year isn't much, about 2.5 centimeters to an inch. But the moon is slowly creeping farther away from Earth. And, you add up a whole bunch of years, like billions of years, and what you get is, moon used to be close and now it's fairly far away. And one day it's going to be very far away.
Yeah, and in terms of reality, we won't see the moon disappear from the Earth Moon system before the sun dies. Okay, it's going to be longer than we have left. It's going to take way more than 5 billion years for the moon to go far enough away so that it's no longer gravitationally bound to the Earth. But that could happen at some point. Now, if the Earth survives the death of the sun, and then in the bathed in the light of a white dwarf with lots of hot ultraviolet radiation, of course, Earth will be sterile and dead, but long since dead. But the moon could drift away over time. Now, anyone coming to this solar system would say, "Oh, look, a dead planet, a rocky planet with no atmosphere. That would be us. Okay, has a moon around it. That's cool. Okay, let's move on." And they would miss the entire civilization that grew here over 4.2 million years from the time of Lucy, and all the life that preceded it. This is
Genghis asks, wonder how often that happens with Jupiter and all its moons. Would they drift away or get pulled into Jupiter? They're outside the so-called Roche limit of Jupiter, so they're not going to get pulled in. It's interesting to contemplate, though, if you've ever heard of the three-body problem. Not the book, but the physics deal. You've got 4 major moons of Jupiter, and they're all tugging on each other while they all tug on the planet, and the planet tugs on all them. I mean, this is why Io has volcanoes on it, is Jupiter and the outer moons are all fighting over Io, and the gravitational tug of war there is the tidal forces is enough to heat up Io so much that it causes volcanism on the planet, on the moon.
Yeah, it's being kneaded like bread dough,
Yeah.
It's being squished and released. And it's not Jupiter that's primarily responsible for that, believe it or not. It's actually the responsibility of the other moons, the other Galilean moons. As they circle around Jupiter, they pull differentially on Io at different times, causing that to happen. Now, the same thing happens at Saturn. Saturn's moon Enceladus is being squished and released by Dione and other moons closer to Saturn. And so Enceladus is a water ice moon that has water beneath the surface and geysers at its south pole and hydrothermal vents at its south pole. And hydrothermal vents are very, very important to life here on Earth. So it's possible that even way out at Saturn, life could exist inside of Enceladus. Europa is undergoing the same squishing. In fact, for NASA's Unexplained Files on Discovery, they actually asked me to create a model showing how that squishing works. And I was able to show how the fissures open up with my model. I had a ball that was coated with this icy material. And as I crunched the ball, you could see the fissures open up and then close up as they kept getting kneaded. All right. And so that was an interesting way to illustrate it. And it kind of, people were able to understand it.
I bet you stuck a wet tennis ball in the freezer, didn't you?
I did not actually. You know what I did? I took a rubber play ball and I coated it with a spackling compound to simulate ice, a very thin layer. And when I pressed it gently, you could see cracks form. And wherever those cracks would form, you could imagine a geyser coming out. Now, they wanted me to call them geysers because this was a London film crew, and they wanted me to say geysers. Mark, we call those geysers in the UK. I went, no, they're geysers. I don't ever say geysers. We reserve that for old people. He's an old geezer, And I said, spelled differently. So we kind of laughed at that, But the simulation really hit home because they could understand how the gravitational pull from various moons, not just the one, is causing that kneading effect. And they have sufficient mass to do that. See? So, same thing with Europa around Jupiter, right? You have Callisto outside, and you have Ganymede. They're big, and their mass is enough to start kneading Io against Jupiter, making that sulfurous moon just squishing back and forth. And then you, of course, have Europa getting kneaded, Kneaded, kneaded like dough, in the same way, getting squished. And that squishing also heats up the interior, which is why Europa's interior is warm because of this kneading process, which is really, really interesting. Without the kneading process, Io would be a cold, dead world because its heat from formation might still be there. There might be a little, but it is a moon, so it's cooled off substantially. But that kneading process keeps it warm.
Let's go look at something else.
Yeah, I know. I'm gonna just looking at that. I want to say hello to Irish Beach Boy. What's going on, man? Yeah, we missed you too, Irish Beach Boy. Thanks for joining us. Cosmic Rays with us. How you doing? Yeah. Well, JWST's Find Array. We talked about that on the last Sky Tour Radio, which was Sunday. So if you missed it, you missed it. We could talk a little bit about it, I guess. But in terms of tonight, what we're going to do is we're going to move to a different object. So there's the beautiful, I mean, this really looks stunning. All this detail in here. Look at this. Maybe we can zoom in one more time before we get rid of this.
They evidently released some new images very recently from JWST of M42 Orion Nebula.
Oh, yes.
Did you see those? I posted them this morning.
I saw them on our group chat, yeah.
Pretty wild stuff.
Daryl, Izabela, and I have a group chat where we share all the latest stuff. Okay. All right, this is great. All right, we're getting some. There's a little wind out there, and so we have that happening. So we got to deal with it, unfortunately. All right, let's go back to a night vision mode here, and then from our night vision mode, we're going to go to something new. There we go. And we'll zoom out. All right. Okay, there we go. All right. I changed the placing of my camera because Izabela said to. She made me do it. So I did it. I always do what she says. Okay. Okay, there we go. All right, now let's go.
Did you happen to see that APOD picture of the red Sprite lightnings?
Oh, yes.
That's the eeriest looking thing. I mean, they look like they're alive.
Yeah.
They said that it lasted like a 25th of a second or less.
Mm-hmm.
But, geez, they were so well defined. They looked like they were organic.
Yeah, the structure.
Yeah.
The filamentary structure. What he's talking about, for those that don't know, sprites are a really interesting phenomenon associated with thunderstorms. And down on the ground, you have thunderstorms, right? But way, way up high, you have oxygen up in the upper atmosphere. And you get these strange electromagnetic interactions with the oxygen molecules up there that make these red spires that are way above the thunderstorm clouds down on the ground. They're literally up in effectively space. So sprites are really cool. I've seen some taken from the International Space Station looking down. That's a cool view. Hello, Izabela.
Hi, Izabela.
All right, this is Messier 11. It's not a globular cluster, but what it is an open cluster, and it's in Scutum, I believe.
Wild duck?
Yeah.
Yes, Scutum, the shield.
Yeah. And so this is what it looks like. There's the shield. All right. And in terms of where it is in the sky, there's our southern sky. Scorpius is just lingering at the low end of the horizon. We can no longer see it now. And now we have this view of it. There we go. So let's check it out, and you'll notice something in particular about this. It's in a very, very high Milky Way region. All right, and so what we're going to do is we're going to just go a little bit westward, pull it to the left a little bit, and we're going to move up a tiny bit because there's a star cloud just down here in the lower right that we want to see. All right, and get a little piece of that star cloud. This looks good. All right, so you'll see searching up there. We're searching for our guide star, and we'll turn off that. We are done with the Omega Nebula, and this is actually called the Wild Duck Cluster, also known as Messier 11. Why Wild Duck? Because I guess someone imagined that you could see a flock of ducks flying here, I guess. I don't know. And it's known as Messier 11. Okay. So, just to give you a little label up there. Hi, Bonnie. Anahata77 has joined us. All right, let's do a 25-second shot of this guy and see the detail that you'll see is rather amazing. There's a lot of really cool detail in here. So we'll skip out of that particular view. There is our Omega Nebula, and we'll clear that for now because it's up on the server by now. And now coming up will be the Wild Duck Cluster. Also known as M11. There it is. Let's
Looks
process.
quite blue tonight.
Well, wondering what time the moon rises.
Arizona time, I think it's about 8:30.
Okay, it's 8:12 now, so let's just color correct this. So there is the color corrected, and you see many orangey stars. A lot of those stars are embedded in dust, and so they look red because of that. But you can see a lot of this dust up here. Okay, really, it's amazing.
Moonrise in Wickenburg at 8:24 p.m.
Okay, so we have a few more minutes before it rises.
Time.
Let's move that down to here. Okay.
I think the blue is nice. It contrasts well with the like the big red star up the upper right. I like it just like it is.
Okay, this is the color corrected version. This is what the actual color is. So, but you see that beautiful red star up there. Now that could be a red supergiant that's far away, or it could be a small star that's closer to us. Not a red dwarf, but maybe a late K star or something like that. I'm not sure, but we can find out. Let's go to our planetarium and let's zoom in. And here is our this is our view. Our new view is 1.5 degrees in length by about a degree tall. Okay. And if we zoom in, there's that red star. What is it? It's a K2. Okay, yeah, see? It's a K2, and there's that Roman numeral 3. It's a K2 star, And it's a giant because it has the 3 after it. The Roman numeral 3 is the luminosity class. So you see it right there. The K and the number 2, that's the spectral class. And the 3 is the luminosity class, the Roman numeral 3. And K23 is the spectral type. So that's how this works. So it is a K star. And this particular star has a parallax. So in other words, we know its distance. It's 1,430 light years away. So it is a giant star that's a little farther away. See that? That's cool.
Genghis asks, so star clusters, are they somewhat stable or are they consuming each other? And with all the stars in there, can they have planets in there too? It depends on the kind of cluster. Genghis, M11 here is a so-called open cluster, and they all formed from a large cloud of, dust and gas, and they're mostly probably similar types. Open clusters tend to fall apart over time. They're together now. They'll be together for a long time, but they tend to drift apart eventually. Globular clusters are a different beast. They've been around for billions of years, and they have sufficient mass and gravity that the open clusters stay together for billions of years. In fact, they're some of the oldest objects in the universe. Could they have planets? I suppose. If those are as hot and blue as they look to me, there may not be anything living on those planets, but I don't see why they couldn't have planets.
The only thing we worry about with young hot clusters is the fact that they have very powerful stellar winds, and so those stellar winds might, once they start forming, once the stars form, they might blow away all the dust around them that might be made into an accretion disk and then planets. So it's possible that there's planets, as Daryl said, but most likely that would be a later development that would happen after the cluster dispersed. This is a young cluster, so I wouldn't think there's any planets in here per se. There might be. It depends on the actual age of the cluster, but you'll see how it's so compact. This kind of implies that it's a fairly young cluster and hasn't been dispersed yet. Like M44, the Beehive cluster, that one is closer to us, but it's actually has fewer members apparently because of the fact that they've started to disperse over time. It's a hazardous area, Genghis, as you mentioned. Hello, Sam. Sam S. has joined us.
Probably is a heck of a view from inside there.
Oh, yeah, you got a lot of bright stars in your sky. A lot of stars like the brightness of Rigel and Sirius, probably, depending where you are. But you are going to be subject to a lot of the ultraviolet radiation coming from those stars, and that would be sterilizing for most life at this stage in their evolution.
We talked about Wolf-Rayet stars last night on the show, and I looked up Wolf-Rayet stars, read up on them a little bit, and the one thing that I think most of them have in common, they are so bright, or they are so energetic that most of their energy is put off in ultraviolet.
Yeah.
And I think you said last night that you need a SPF 10 million probably to survive even a minute.
No, you'd be I think you'd probably be vaporized in seconds.
Yeah.
You wouldn't even. Yeah, any kind of organic tissue would be immediately ripped apart to the molecules by such radiation, because there's no way to handle radiation that's millions of times stronger than the sun.
Yeah.
And in other words, it's likely too that any planets that were in the vicinity, and if the star wandered into the neighborhood, any planets in the vicinity around other stars would literally probably be vaporized slowly. Depending on how close it got. And that's a question that people like to address is like, how far is safe from a supernova? And there have been some papers I've read lately, actually, that say, 150 light years, 30 light years. And they cite all these reasons, and they assume a 30 mass star, a 10 mass star, 10 solar mass, 30 solar mass. And it turns out that the bottom line is you don't want to be near a supernova no matter what. Okay, no matter how far away you are, the safe distance seems to be literally about 100 light years. After 100 light years, there's no star out there that could go supernova that could hurt you in a sustained extinction level event way. But it's about 100 light years, and that's on average. So if we had a supernova go off 7 light years away, let's say Sirius did that. Sirius like 8 light years. Sirius can't go supernova, but let's say it did. If it did, then you might find that our Earth would be bathed in gamma radiation, X-rays, and there might be an extinction level event that would happen here because of that. But there are no stars in our neighborhood that can cause this, so we're good for now. Doesn't mean we'll be good forever, because we check the paths of nearby stars and going around the galaxy, and we know what stars are coming close. We know what stars are going further away, and one of the stars that's getting closer is Barnard's star, and Barnard's star is a small star. It's not it's an M dwarf star, a tiny little star. It might have planets. Supposition is that may, but if it's going to come about as close as 6 light years to us, keep in mind Alpha Centauri is 4.3, and it's going to get a little bit closer than 6 light years, then start going away again. So studying the motions of the stars give us this data to be able to plan for an eventual problem. And if there was a problem, we'd have to get off the planet. We'd have to leave. And that's okay. I don't mind that. I think eventually we're going to be a spacefaring race anyway. So it'll be kind of interesting to see that all come to fruition. So
Can we zoom in on the cluster some, please?
Yeah, sure. And Ray says, so Betelgeuse explosion won't crispy critter us. No, it will not. In fact, it'll be the fireworks of the century. Really enjoyable to see. Okay, so we zoomed in a little bit. Let me drop this down and check out a little more detail in the cluster here.
They might just be foreground objects, but it does appear that there are some reddish stars in the cluster. We've seen this in the double cluster in Perseus too, that some of them, actually are in the cluster, part of the cluster, and the stars are old enough to have evolved from, they're heading toward red supergiant stage.
Yeah. Well, we'd have to look and find out more details on it. It is true. If you look at the wild duck, its distance is 1,900 light years, and it has more than 100 stars in it. And its magnitude is 6.3, reduced to 6.49 by 1.48 air masses in its current position. we'll talk about air mass some other time. That's something I had to deal with a lot. It was really a problem. Oh, C&D Boy, finishing up the volcano show with Dr. Fox 2000. Excellent. Dr. Fox 2000, excellent channel. If you get a chance to tell him we're thinking of him, C&D Boy. Maybe he'll drop in and say hi. He usually does.
It is pretty cluster.
It is. Let's see if we can go even closer here. Yeah, a little bit of... got a little bit of... let me try and drop this down. Wow.
There's a few quite red ones in there.
Yeah, but if you look around, you got all these red ones, and you don't see an increase in red ones. It's almost like it's a veil, not in front, but behind, and we're seeing these stars through the cluster. Perhaps we gotta check those out. You see what I mean? There's a lot of red stars in this vicinity. Maybe these are all in the cluster. We don't know. It would stand to reason that they could be, because the background stars are a lot smaller and less luminous. But they're there. That's making up the bulk of that orangey color you're seeing on the screen.
I mean, they're cool. Inside the bounds of the cluster, so maybe they are.
Well, we don't have to say that it's just within the bounds. I mean, this star out here could be in the cluster. This star, these two could be in the cluster. And we don't know, because we can't turn this universe sideways and see if this cluster has all these additional stars in it. And what we're seeing is stars that have drifted. Depends on its age. Depending on its age, we expect a certain amount of drift based on the N-body problem, as you mentioned before. And the drift, that's yet another.
Yeah, but again, I think, it's like the double cluster in Perseus. Some of the red stars really do belong to a cluster.
That's right.
It'd be fun to see. They're evolving.
Yeah. It'd be interesting to know. I don't know the direct answer on that. Cool. All right, well, this is M cluster, M11. We're going to save that now. All right, and we'll save it exactly as seen. So we have the Omega Nebula and Measure 11 now, and we can take that label off. And we will see it one more time when we come back. Let's just go back to our night vision mode so we can see what's going on here. There we are. All right, and now let's go find another object to check out. And I'm thinking, let's zoom out a little bit first. It's 8:28. I'm going to guess the moon will just be rising. We look over here. Yeah, there it is. It's on the horizon. Alright, so what we'll do is, let's check this out. Let's see if we can view the Andromeda Galaxy right now. Well, we might be able to. Shall we try it? Yes, we shall.
Sure.
Why not? It may be just out of reach, but we'll find out.
Gungus asks, could there be some gravitational lensing from the cluster? Maybe very minor scale, but typically when we see gravitational lensing, you're talking like galactic scale or galactic cluster scale stuff.
That's correct. Gravitational lensing is an interesting phenomenon, but usually, as they'll just point out, we see that when you have a foreground cluster of galaxies, and if you have another set of galaxies behind that cluster out here, okay, or sorry, this is the foreground cluster, you have this other one here, this galaxy cluster could warp the light from this distant cluster or vice versa. Okay, you could see a warpage occur, but it's always the more distant one that's getting warped. So it's really interesting how that functions. And the gravitational lensing is very evident in some of the James Webb images of the deep clusters out there, and very, very obvious. Another thing that's true is that, and this is fascinating, is that it turns out that there were a lot of very interesting. Let me just pull us back here first. There was a lot of galaxies that the Hubble saw that they concluded were actually elliptical galaxies, much like the ones you'll see here in the Andromeda Galaxy. But with the James Webb, they were able to see that they're actually spiral galaxies. They just were not visible to Hubble. This is an elliptical galaxy right here. Okay, it's a companion galaxy to the Andromeda Galaxy. We're going to just go west. Our field of view is now so much smaller. Again, it's only a degree and a half across now instead of the 2 degrees across. Okay, so we're going to just come up a little bit more, and we now can only get half the galaxy in, which is great because that means that we can focus and detail all kinds of detail. It goes this way, kind of goes in this angle. You can kind of roughly see it. We'll head west a little more and put the nucleus up in the upper left a little bit. Yeah, this is good. You can see from our bottom view here, the telescope is pointing over the roof. It's an illusion here showing it looks like it's pointing at the roof, but it's not. Okay, so we're going to just drop this down and go to the west a little bit more again. And then we'll grab our guide star and go to town. In fact, if you look in this view here, this right here, right there, this guy right here, that tube, that additional tube, it's a small tube on the big tube here. That small tube is actually the guide telescope that you're seeing. Actually, that's the pointing didn't come out right. This is the guide. Let me just move my chair. The guiding telescope is up top here, right on top, right there. And this is the big main tube. I should have just enlarged it to show you. Okay, we got our guide star finally. So you'll see this elliptical galaxy here, and then here is the rest of the galaxy. The Andromeda Galaxy is pretty high, so this might look pretty. Let's do a 35-second shot here. Hopefully, I don't see any wind hitting us yet. We do have the moon out, but it's still low, and it's not full anymore, so it's going to be actually dramatically lower light. So let's go in here, and the last shot we have is Measure 11. That's in our image buffer right now, and we'll get rid of that. Be gone. And now we're waiting for the Andromeda Galaxy. Andromeda is a beautiful galaxy. It's over 2.5 million light years away. So it's really it's like 2.5 million light years away, and then right next to it is the Measure 33 down here in Triangulum, and that is the Triangulum Galaxy. That one is also 2.7 million light years away. Okay, so the blue is from the moon. All right, but if we color correct, which we can do, all right, we have that, and now we can do a little processing here really quick to start kicking up the detail. Look at that. You see this beautiful dark nebula? All these stars you see here, these are in our galaxy up here. Okay, we're seeing the Andromeda Galaxy way out here, 2.5 million light years beyond. Okay, so we're seeing through a veil of our own stars. And if we come down here to the bottom of our own galaxy, to the bottom of our own image, you'll see this beautiful blue arc here, this one here, that one there. These are hot blue stars in the disk, which is where young stars form in a galaxy, because that's where a lot of the activity is going on. That's where a lot of the shock waves occur that generate these both the spiral arms and star formation. Interactions with other galaxies does the same thing. Let me just name this now. The Andromeda Galaxy. And it's also known as Messier 31. Cool. We call it M31. One of the things that I find interesting about these objects, and I know Daryl does too, is that, is that when we look at something like this, you can't help but wonder whether there's someone else with a similar telescope looking back at us going, and this is the Milky Way, this is Galaxy, and they'll give it its own name. Milky Way Galaxy is our name, but they'll name it something else. And I'd be interested to know what they think we look like from there.
Maybe look a big fried egg.
Yeah, there you go. It might be, yeah. Look at that. Let's color correct again. And my dingo is with us tonight. She's in behind me. And Izabela says, and was wondering, are there absolutely no stars between galaxies? Aha! That's my wheelhouse. When I was getting my astronomy degree, I actually did my thesis on runaway B stars, B-type stars, and these B stars were actually leaving our galaxy at high speed, and that's because they were flung out of their respective clusters. Like this right here, this is an OB association in the Andromeda Galaxy. That's O and B stars, and they're forming quite close to each other, and they might have a gravitational whip, and one of them can get flung out. And I found a number of stars speeding out of our galaxy, that were B-type stars. So that is a possibility that you can have stars between galaxies, but it's actually very, very limited. And so it's something that is a great idea, Izabela, and that's really cool. Look at this. This is really pretty. Let's work on getting some more detail out of this.
So you used to be 2 by 1.5 degree field.
Yeah.
And now you're 1.5 by 1 degree field approximately.
That's correct.
Yeah.
With almost twice the resolution.
Yeah.
So
you do a mosaic, you're going to have a lot more panels now.
Not a lot, but yeah, but that's okay. It's going to be a lot more fun to do them because each panel is going to have a lot more detail.
Oh.
Here, let's drop this down so you can get a little better look. So there you can see the hot blue stars down here. Let me take you and move it over. Okay. Let me grab you. Move you over here. And you stay there. Don't move now. I want to thank all of our patrons that have made this possible. Okay. John P. Izabela M. Ollie B. Chief McCyber, Vera C. Ronald T. Martin W. Raymond B. Cindy M. Susan W. Diane H. JSCO 77. And we want more. We got to have more of you to join in here. We're doing this for nothing. And we're trying to keep it real and trying to keep bringing the universe live in real time. But if you could only imagine what it cost us to do that you see right here. Holy cow. I'm glad I didn't charge people, up front, because if I did, our subscription rate would be exorbitantly high. People wouldn't be able to pay it. So we're trying to do this without doing that. Cosmic Ray's asking for a nebula there, Daryl. Cosmic Ray, we may need a moonless night for that nebula. So I'm not sure that would work. Hey James, how are you? James Hyatt's with us.
I see that. I've never heard of it before.
Okay. Let's try to drag some more detail out of this. Look at that. That's really pretty. Now, I do have enhanced detail on. Look at all the convolutions in the core here. If we turn off that enhancement, it'll get a little bit more muted, but you'll still see it. Yeah. I'll leave it off for now. Okay, let's go back to our colors and histogram, and let's color correct again. There we go. So here's that elliptical galaxy, see? Now, if we zoom in on that, you'll see that it kind of looks like a featureless blob. Okay? And that's something that we recognize to be the case with these particular galaxies. They look like featureless blobs. However, the James Webb showed that some of these supposed featureless blobs actually have spiral arms that are in the infrared only, and you can't see them in visible light, at least not yet. So that's for those galaxies that are very, very distant. Okay, redshifts that it's called over 10. That means it's very, very far away. You're welcome, James. He said thanks, everyone.
Ray, Strautner Drexler Sainte Object 1, that is the large arc of oxygen 3 emission that Bray Falls found near Messier 31. I do believe. It sure looks like it from the picture I found.
Yeah, we'd have to do deeper, long exposures to capture something like that. And it has to be a moonless night for that, Rake. And the reason is because oxygen 3 is greenish blue. So we end up with this false blue background because of the moonlight. The moonlight's actually causing a small blue sky effect like we have during the day for among similar reason. It's scattering the high frequency light that is reflecting back off the moon to the Earth. The atmosphere is, and so that's why we have blue sky. It scatters the blue high frequency light. Well, that's happening with the moonlight too. That's why there's always like a bluish light around the moon, okay, and not a different color. And that's why I keep having to color correct to get us to the right colors. See, now we have a more of a black background, and you see the blue in here for the stars. But this is beautiful. You can almost see that disk of the galaxy in 3D. That's really something. Wow.
Michael, the density of the galactic center is much, much greater than what we're looking through here. There's no comparison. I mean, it's like we're looking out through the suburbs compared to being downtown in the center of the galaxy.
Oh, yes. We might be looking through a piece of the Cygnus and Perseus arms of our galaxy. Just a bit, because we're kind of looking between both of them when we look toward Andromeda. Hello, Gabrielle. How you doing? Thank you so much for joining us, Gabrielle. You have a good night. Look how pretty this is coming out. Holy cow. Look at all the detail.
Oh.
And that's sharpening. It's off. Let's turn it on. Okay, and let's reduce it down to 2.28. So now that's a reasonable compromise. Wow, that's really something. Really
Izabela,
nice.
professional observatories, they can pick out stars in Andromeda Galaxy. I don't think they have the capability of seeing planets around those stars, though. Not
Yeah,
yet.
we can't see planets actually around stars in our galaxy yet, except for some rare cases.
Yeah.
Like one of the Henry Draper catalog stars has a retinue of like 4 planets around it, which they were taken by the Gemini telescope direct imaging. But you know what's funny is you look at the smallest possible star you can see here, and any planets around it in our galaxy are going to be totally well within the glare of that star, that light that we see, that tiniest of points of light. If it had planets, they'd be well within that glare. So it's really, really hard to physically see planets, and only in a very few cases have they been able to do that. This is the best Andromeda Galaxy we've done, because you can see all this detail. This is going to be gorgeous. Look at this star cloud in here. Look at that. Okay, I mean, when you look over here and you look right here, you see you see this beautiful cloud, this line of stars right here. That is really something. You know, it comes down here. Okay, see that? That's amazing. Right there. That is really quite nice. Yeah. That's right here. So we're actually seeing stars in this distant galaxy, but we can't just see singular stars, not without a telescope like the Hubble. So we are forever going to see separate groups of stars, but no individual stars. We'll see close associations, but no individual stars. It'll always ever look like a cloud to us, except in very, very rare cases. Nice. Oh, this is pretty. Maybe after this I should do frames up above and do the whole galaxy.
Duh.
What?
I assumed you were going to.
Well, okay. Well, yeah, you're right. I was.
I mean, I assume that's M32, the satellite we see below the nucleus of,
Yeah, that's it.
Because it's not as oblong as M31.
Yep.
Which will be out of view, out of field, up above.
Yeah, and
even then, you're missing some of the lower right of the galaxy.
Oh, yeah, we are. Yeah, I'm just trying to get the bulk of the disk right here. Okay, yeah. We've saved it and saved the raw file and the PNG, the visual file. You want to see these? Go here. Go to skytourlive.org, right here at the bottom, and scroll down, and you'll see Take Me to Really Cool Pictures, and it's going to take you to the site where you can actually download these very pictures, seconds from when we took them. Okay, they're all going to be there for you. All right? And don't forget, check out our Etsy store, Sky Tour Shop on Etsy. Sky Tour Shop has all kinds of high-end professional products like this one. This is our Rosette Nebula stainless steel tumbler. And it's really cool. I just had some Thai tea in that one. Okay. There's 25. We're going to save this and save exactly as seen. And now, let's do the other half. It'll be interesting to see what the other half looks like now. I haven't imaged the other half yet with this telescope, with this camera. Very nice. Alright, so let's go back to our spotter mode, or what we call our night vision mode. And now we'll go north. Here we are, and you'll see Messier 110 show up. There it is. Right here. There it is, right there. Interesting thing about Messier 110. We may be missing a little bit of it here in just a minute. But that particular spiral galaxy is one of the few that actually has a little bit of a dark lane of dust in it. And we saw that not too long ago. In order to see the galaxy, we're probably going to end up... Maybe I can just squeak it in here. Leave it there. And go north a little bit more. Like this. Alright. Okay. We'll do this. We're still going to miss some of the galaxy off the edge. It's very big. Alright. So let's do that. Let's move that down a little bit. There you are. Just a little bit. Come on, you. Down a little bit. Okay, good. And that's good right there. Alright. So now there is Messier 110. It's faint right now. And here is this nucleus of the galaxy, which we saw before. And here we'll see this. So, again, we're going to do another 35-second exposure. And drop in to our live stack again. And you'll see the last shot we did. So we did this one, and now this is going to be way down here. And we'll see what's up to the upper left. Alright. So that's really cool. And again, these beautiful hot blue young stars. Look at this nebula down here. Holy cow, it's really showing well. I'm glad we did that. That was lost to us. Lots of nebula in here. See that? Alright, let's clear that. Because we have 3 seconds until next. Let's do that. There we go. Now, in this view, there are, in fact, another OB association up here in the top, and nebulae that are up here in the top that are really interesting to see. And we'll see those now. So we can drag it down here, and you'll see it goes well off there. Okay, let's just process a little, darken things up, start to show off what's inside. There we go. Let's actually go right to the peak of our... There we are. Right to the peak of our curve. And we'll have to color correct all along the way here. Luckily, the desert winds haven't started up tonight. And it could be because the temperature was not as hot out there today. It's the upper 80s. Thank you, Ray, for putting up that infrared image. So, look right here at Messier 110. Do you see? It has a little... Right here, you actually see... This is Messier 110. Right there. And I'll zoom in now just to kind of show you. But you'll see that it actually has a dust lane in it. It actually has a dust lane. Look at that. Very cool. Very interesting. Because we've always been taught that elliptical galaxies have very little dust in them anymore. This is a very, very dense area up here. This is going to show beautifully in a little bit.
Mark, excuse me a second, please.
Sure, we'll be here.
Be right back.
Be right here. Look at that. Wow. Let's see about making the background a little bit darker. I don't usually come up to the top of the white curve because then after we go past that, you see we're losing data. But I'll just go like to here for now. Alright. And then drag this down just a little bit. Alright. Hi, Gladys. Hey, Rhiannon. How are you? So good to see you. It was so much fun working on your film about Tom Reed's incident. Feel free to plug it here in the chat, why don't you? So good to see you. Smile for you. Okay. Yeah, there we are. Look at that. You can see it goes off the edge there. Rhiannon Alley in the chat there. She's a real sweet lady. She is doing a film on an incident that occurred up at a covered bridge up in Sheffield, Mass. Yes, Izabela, a film about Tom Reed. Yeah, well, I'm in it. I have a tiny little mini part. You see me, I kind of come in and go, hi. Can I just say this is the first time I've been on television? And they said, no, there isn't time, and they made me leave. Rhiannon says, absolutely good to see you, and see you soon. Going back to Sheffield in 3 weeks. Oh, very cool. Gotta do pickups out there or something, or just more? Yeah. So we're letting this develop out here, guys. Let me see if I can grab a little more detail. Yeah, look at those star clouds are coming in really nice at that end of the galaxy. Oh, wow. We always need a little overlap when we do our mosaics like this. And this will be the first mosaic. Look at that. Wow. Individual clumps of stars showing up now. Again, that's 2.5 million light years away. And 2.5 million light years away means that's how old the light is. So you think about this and think how 2.5 million years ago on the planet, what was happening here. Okay, Lucy was around 2 million years before that, and so we had the early hominids roaming the planet 2.5 million years ago, and evolution was in full force. And during this period of time, we still had a bunch of different life that's now extinct in our oceans and on land. Wow, look at that. This shows up now. Couldn't wait for this. This here, that's a nebula, like an Orion Nebula complex in that galaxy, but seen from here. Here's another one right here. Okay, another very large one is right here. See that? These are all nebulae in their own right. And then let's see. Just barely seeing this one that's in the other shot too. And if we want to relax this a little bit and give us just a little bit more leeway. Welcome back, Daryl.
Thank you.
That's really pretty. Okay, and if we let it decide what it wants to do, it puts us here. This is pretty. I mean, you can see this nebula complex here. You can see this OB association, and it also has a nebular complex within it. Wow. Again, the universe live in real time. It's amazing. Ray's talking about M110, this dwarf elliptical over here. Again, now you can see the dust and the circulation in there. You see that, Daryl?
Vaguely.
Yeah, that's actually that's something that
I see a sort of a dark lane over.
You got one here
on the left side.
Yeah, see that one?
At
Filament.
about 8 o'clock. Yeah, okay, I see that one too. Yes.
Yeah. Now, as I said, ellipticals don't usually have dust in them, so this is really kind of interesting. Hello, railroad engineer. Oh, thanks, man. He says he's in awe of the new camera. Yeah, me too. Me too. I guess we're going to have to rephotograph everything we've ever done. The moon's already risen, so we have a little bit of the background light pollution, but I can kind of kick a lot of it out by doing things like this and by color correcting right here. So there you go. And the color correction when the moon's out will tend to make things look a little more red, so I can do that to kick it down. Look at this beautiful view up here. Obviously this extends further, but we got this beautiful nebula, as I mentioned. We have a nebula in here, okay, within this nebula complex, within this O and B association. We've got that. And when we say OB association, we're talking about O and B stars. O stars are the hottest stars in the universe. They're also the most short-lived. B stars, less so. But you've seen B stars and you know all about them. Why? Because all the stars in the main Pleiades, Pleione, Merope, and so forth, Taygeta, they're all B-type stars. They're hot and they're blue. Their O stars are exceedingly blue, and most of their radiation, the bulk of their radiation, is in the ultraviolet and the invisible spectra, part of the spectrum. So with the OB associations, we're seeing extremely populous areas in here. This star cloud here is less blue than the one at the bottom, so it's possible that this is a standard star cloud in the galaxy's arm. But we do have nebulae within it, and those nebulae are what we call the stellar nurseries, right? And as we move down in here, the core of this galaxy is actually more of this color. It's more of a yellow. But again, doing color corrections while the moon is out will cause us to have slightly redder looking imagery. This one will be okay doing this way. Yeah, I'm gonna try and manually correct. So do it again.
Asher Rial asked about seeing into the past when we look at Andromeda Galaxy.
Mm-hmm.
When we look at Andromeda, is it safe to say which end or which side is closer to us?
We do know that. I don't know that. I don't know if we're looking down on top of it, meaning this would be closest to us, or we're looking at this end, which is closer to us. I'm not sure if it's like this, okay, or like this to us. Okay, if it's this way, then this part here would it's an illusion. It might look like it's closer to us, but it's actually this part, the upper part. So maybe that's closer to us, maybe that's closer to us. You can see it both ways. So I don't know which way it is.
I was just wondering. I mean, I told
question.
him, 2.5 million light years away, 2.5 million years ago, but Andromeda is a very large galaxy, and you're seeing quite a difference in time considering the orientation. You're probably seeing several 100,000 light years from one edge to the other edge.
Yeah, and it means
farther away.
The nearest edge to us is the more recent time, and the farthest one, of course, is the more distant time. So even looking at galaxies, unless they're face on to us, like Messier 101 is, and like Messier 33 is, which we're going to see next, okay, unless you're seeing that, okay, then you have to make the assumption that we're looking at a galaxy that's shifted in its time. We're seeing one part of the galaxy at a certain time and one part of the galaxy at another time. Same with our galaxy. When you look at Orion, you're seeing, like the belt of Orion, you're seeing it as it was 1,500 years ago, because those stars are relatively nearby. But when you're looking at the Andromeda Galaxy, everything you're seeing on average is 2.5 million years old light. On average. Wow, look at this though, isn't that pretty?
Mm-hmm.
All right, just a couple more exposures and then we'll move on to Messier 33. Messier 33 should be high enough by now. Let's go check it out. It's going to be a little deeper in our trough right there. So we're here, and the Triangulum Galaxy is here, and it's at an altitude, oh boy, 37 degrees. It may be looking into the roof to see that one yet. May have to wait on that one, which is okay. We'll make that for a different night, because we're rapidly losing our evening of views because of the moonrise. But we'll check out a few other things. Hey Ray, let's go up in the Cygnus and look at the Veil Nebula. Yes, it's interesting when we look at our exceptionally beautiful sky. We can clearly see that there are many objects out there that are just literally just waiting at our doorstep to see. Just stunning stuff.
Izabela asks, when is the Flaming Star Nebula coming up?
That's Auriga, and Auriga is going to be Auriga is like a winter constellation, so that's going to be down here.
Yeah, Capella's up already.
Yeah. That's about 4.5 hours away to be at the threshold of visibility for us. Let's go back to this. Look at that. Holy cow. Wow, that's 25. All right. So we're going to save that to the same place and save it exactly as seen. Look at that. Wow. That is really, really something. I have to say, I'm very impressed with this camera.
Yeah.
It's literally one of the better ones that ZWO makes. Wow. Look at this beautiful nebula complex in here. That was invisible to us with the other camera. This camera is tuned to this particular scope, okay? So I spent the time to calculate what we need for a camera based on the number of arc seconds per pixel that we'll get to see. And this camera brings us in with views that are considered very good. The other camera was just fair to good. These are very good. So it's a very, very different approach. And you can't just put the camera with the best resolution on the telescope and get better results, because you could do something called oversample your data, and we don't want that either. Okay, so we got that, and we'll get out of here. We'll view that after we saved it already, of course. And now let's go and look at least while we're in the neighborhood, let's attempt to see if we can look at Messier 33. I don't think it'll be in a position for us to see, but we can try it. It might be a little low, but let's try, shall we? Okay, let's bring that in the center. It's only a little bit south, but it's might be south enough that it's... There goes the telescope, look. Oh, that's close. That's really close. It'll be in the view, but I'm not sure it's right there. I'm not sure. Let's find out. Let's go a little north. There we go. Well, we'll give it a shot. If there's any red glow, it means that we're looking at a part of the wall of the observatory. But we'll give it a shot, because this galaxy is absolutely stunning. And we capture the entire thing. It's face on to us.
Does the new camera have a red light on the end like the old one did?
Yeah, it does.
Huh.
Yeah. Well, that's the power light, you know. And most
I
of
understand, yeah.
well, for people to understand. And because the camera's on the front of the telescope, guys, we end up having a red light that's tiny LED that's looking out and actually playing out on whatever is in the field. And if the edge of the building is in there, the camera's so sensitive it picks it up. Now we're also running the camera at minus 17 Celsius right now. We have the cooler running at 100%. It's actually shouldn't be at 100. It should be less than that. But because of the big temperature gradient out there, from like 93 degrees during the day, we have to deal with that. Okay, so let's see where we are. We're actually pretty well centered. That's good. All right. So now let's go and do a 35-second shot here. We are guiding. Let's see what we get. All right.
That's interesting. Infrared data from the 2-mass survey and the Spitzer Space Telescope showed that Andromeda is actually a barred spiral galaxy like the Milky Way.
Interesting, because it's still an B, little b, in the designation. So that'll change, I'm sure. Okay, let's see. If there's any red in the image, we have to wait longer. Oh, a little bit. See that? That little bit is enough to cause us to miss, unfortunately, it's, this part's above the thing. This part is below the wall a little bit. So we are just impinging a little bit on the wall. Okay, well, what we'll do is we will see about coming back to this. That might work. It's only
Interesting.
midnight.
What jumped out at me in that image, it was quite a line of stars on the galaxy that I don't recall ever seeing before.
Wait, in this one? Or
Yes.
in...
You see, from the nucleus of the galaxy down below it, from about 7 o'clock over to 5 o'clock,
Okay.
there's like a row of 4 or maybe 5 stars.
Not here.
Farther up.
Probably. Oh, these guys. Oh, I see them.
Yeah.
That's
I don't
interesting.
remember ever noticing that before.
Yeah. Well, we'll come back to this one, guys. Right now, I have another idea. Because we got the stupid roof in the way. That's okay. I don't complain. Let's go check out one we have not looked at lately. The elephant's trunk. You know, watch the telescope move now. It's going to be looking... This is the North Pole right here, so it's going to be looking just above the pole. So let's go back to our night vision mode here. Okay. All right, and what we're going to do is go westward a little bit. There we are. So the nebula's in here. I just have to work on our placement. That's all. And so I'm going to drop this down. Because I think this is our black cloud that we like so much. And that's a little too far. I think the elephant's trunk is right here. Right there. And I might be wrong. Okay. Alright, we're going to go right here. We're going to try just a test shot here. And we'll do 35 seconds again. And see what we've got. Actually, I don't need 35. I just need 20. Yeah, there it is right there. Okay. We got it. Good. Alright. So, what we're going to do is we're going to move over just a little more in order to frame this nicely. So we're going to move a little bit to the west. Because we want to catch the caravan as well, which is to the right.
Mark, Izabela did a mosaic of the two images you did of Andromeda. It's in your chat if you can pick it up.
Let's go see. Let's go see. All right, let's okay, I see it. Okay, first things first, let's get the exposure underway here. This will be a 35-second shot. We had to wait for our guide star anyway. And there we go. And now we'll come in to our live stack and see that last image that we saw. That's the top of the observatory getting in the way. But now we'll see this. That's actually a pretty shot of the Andromeda Galaxy. So we'll, and I'm gonna figure out a way to show this in just a second. Let's see. First of all, let's do this. Oh, wow, that's pretty. Even with a partial moon out there, we're starting to see some detail. Let's jump to the top of our data curve to kind of bring out the contrast. This is the elephant's trunk right here, and this looks like the humps of a camel, so they call it the caravan. This is a good composition. That's what I was looking for. Okay, drop a little bit of the blue out of there. There we go. Okay, and now let's see what we can do here to show Izabela's image. Izabela does such fine work for us. If you look at Instagram, Twitter, and other let's see, Instagram, Twitter, and I'm drawing a blank. TikTok, you'll find some videos that Izabela's done for Skytour Livestream that are really cool. Let's see if this does it. Alright, hold on one second. I'm gonna... Okay. We'll keep looking at this for now. Alright. Let me try this. Maybe this will do it. We'll keep that going. That's really looking pretty. four images stacked so far. That's an interesting region too, for reasons we'll talk about in just a minute. Uh-huh. Okay. I am unable to show that image right now.
You want me to drag it into your?
I have it. I have it. I just can't, for some reason, can't get it to show. I don't want to go to a dark screen here, but let me just. I'll try one more time. All right, bear with me, guys. I'm going to try and show. This. Let's go here and see if I can. I don't have anything there. Let me just add a source. Actually, I don't have to do that here. I can come back to this guy here, let you guys watch this. I can try this in the background while you're doing that, while we're watching that develop. Okay, we'll try that. All right.
Okay, I just dropped it in your chat. If you can't,
Okay.
we could cover it otherwise.
It's all right. I have been trying to capture it. I don't want that. Whoa,
I had
good.
to.
That's wild. Look at that.
I had to save it to downloads.
Okay.
Okay, you should have it now.
Okay. I saw it in the Skype, so I haven't grabbed it yet. I mean, okay.
It's in your chat.
Okay.
Our chat. You're in my chat.
Yeah. Okay. Well, we'll just watch this develop right now. See, we don't have any commercials. If we had commercials, then I could do it during a commercial break. But in time, I mean, if we end up with some sponsors, they might actually be pretty cool about doing that. Let's I'm gonna increase the contrast here a little bit. There we go. That's to make this image a little darker. Okay. Izabela, that's a very beautiful mosaic, and I will figure out a way to show people. I know I can do it. I have a great idea how to do it, actually. So let's do this, and let's do this. Okay. Alright, and now, all I have to do is, I know how to do it now. Okay. While we're letting this develop, oops, sorry, don't mean to do that. It's 67 degrees out there, as you saw. So while this is doing that, let's bring up this guy. You can't see this here. I'm going to bring up an application that's going to allow you to see this beautiful image that Izabela put together for us. Oh, there it is. I'll do this. Okay. Well, I told you, Daryl, no drinking on the job.
Oh, yeah.
Okay. We're ready here. I'm just going to... Here we are. Where is my...
How dry I am.
How wet you'll be. Okay, I'm gonna delete that then. Okay, we're up to 13 stacked for this. And that's gorgeous, isn't it? We'll talk about that in just a minute. Add source. And there it is. Okay. Well, there we go. That is the beautiful Andromeda Galaxy that Izabela made for us. Look at that. And we can, zoom in on the different aspects. We will be, when we do our professional processing on this, sorry about that. We do the professional processing on this, and you'll see some amazing differences here. We're going to be able to show a lot of the... I'll do it this way. There we go. So that's the extent of the entire image right there. All right. There we are, right there. And so we'll show you all that. And this over here, you'll end up seeing a lot more detail in here, which is really cool. And then you'll see some other detail, but you'll see that in a lot more detail. Promise.
Well done,
Okay.
Izabela.
Yeah, very nice. And fast, too. It's something that we now can do pretty easily, which is nice. All right, let's see where it wants to go for the processing. Oh, look at that. Let's zoom in on the elephant's trunk itself, shall we? Look at that. Say, inside this elephant's trunk, really interesting location. There's a red star in here with a tinier red star. Now, the color might be reddened by dust, and certainly is to some extent. But one of the things to notice here that's really important to notice is that this image that we're seeing, this has it's like a cavity in here, and that cavity is typical of young stars. When they're first born, they actually have copious amounts of stellar wind, and M-class stars are really kind of the worst offenders in some ways. They have flares. They're flare stars a lot of the time. And so when we look at this, all right, you look at this star, and what's happening is it's blowing out with stellar winds, blowing out, and it's actually pushing away dust and gas nearby, opening up a cavity around itself. It's almost like it's destroying the nursery within which it was formed. Ungrateful stars. So that's interesting how that works. And you see, like with the Rosette Nebula, our Rosette that I showed you before, cavities opened up in the middle here of our Rosette Nebula. We'll be able to show you the Rosette in a couple more months because it's rising. So really neat. Let's do one thing here. Since we're going to be happy with this for a moment, let's actually get rid of our telescope view and just go into full screen. Look at that. That's really pretty. Really pretty. And if we come up here, you'll notice that there's dark nebula up here. This area here is really interesting because we have our elephant's trunk over here, right? But this guy right here, this is a very interesting dark area because this is very dense. And this dense area is probably an area where stars are being formed right now, and maybe planets in there, because this is cold and dark. This cold, dark nebula area, and these areas over here, and those over here, and there. Okay, these areas are very, very prolific with star formation, and the James Webb can look inside of these dark areas and see, in its far infrared, it can see the heat of young stars forming in there. That's how we have seen many such stars as of late. So it's pretty interesting that we can see this stuff and that the James Webb can show it to us. But as I've said, the dark nebulae, that's where it's at. The fundamental building blocks of life are made in here. I've mentioned this before, these dust grains in here. This is dust we're seeing. Okay, these dust grains, you'll see a fringe maybe of red around there because it's mixed with hydrogen gas like you see here. Dark dust, all right here, dark dust rimmed by a soft red glow. That's because there's a dense layer of dust in here, and certainly there is hydrogen gas mixed in there, but the dominant glow is created by the very thin layers of gas outside here, because this dense dust overwhelms the red glow because it's buried behind so much dark dust. That's why so many times we see nebulae like this, dark nebulae fringed by stuff like this. A famous location is the Horsehead, okay, where this occurs same way, and other nebula we've seen. All right, the Pillars of Creation, the Omega Nebula that we saw.
That's the caravan.
That's right. This is the caravan feature of this. Let's move this up into the view because there's a lot more to it. Okay, so this dark dust then is really where it's at, and so the dust is carbon molecules. You know, carbon has 4 electrons in its outer valence shell, it's called, and those 4 electrons can bond with many other things and form many different compounds, the most of any other element in the entire periodic table, although there are elements that have more than 4 valence electrons in its outer shell, but carbon is the most flexible, and so it stands to reason that life is a carbon-based process. To me, I'm a carbon bigot. I've told you that many times. So I guess that means I'm racist against anything other than carbon, I guess. And I am. I think that, the nearest competitor would be silicon, because that vertical column is what we care about. And below carbon is silicon. But silicon tends to make crystal structures that are very, very robust. Okay? I've mentioned before, you walk on the beach, you're walking on silicon dioxide, a silicon molecule, and 2 oxygen molecules. Interesting that 2 out of 3 of the atoms you're walking on the beach are gas. It's kind of interesting. So I think that's pretty cool. So these dust grains then will get formed. You'll have silicon atoms that bond with each other out there. You'll have carbon atoms making carbon-carbon diatomic carbon atoms. What?
There is a star directly above your pointer right now. It's a white star. It's at about 4 o'clock right there. That star appears to have a tail on its right side.
It does. That's real.
Is that reflection nebulosity or what's going on?
Is.
Can you zoom in on that?
I will in a minute. And it goes this way too, actually. So going back to what I was saying, carbon atoms, you can have a carbon-carbon molecule and silicon molecules, and then they accumulate other materials on them in the form of ice. And these ices are the things that literally are the building blocks of life. Let's see if we can bring out that reflection nebula a little stronger now. Okay, and then pull this in a little. And this should be good. Yeah. So there you can see it. And we'll zoom in on it now. So you can see. Yeah, we've seen this before. That beautiful wispy structure. Again, this is what you see when a star has its light scattered by the dark dust you see here. Okay. Many times these dark, dusty regions will be rimmed by a blue glow, like we see in other nebulae. And in this case, there's a wisp of dust that is scattering some of the blue light from this star right here. And So that's high frequency light.
I don't remember seeing that before.
Oh yeah, we've caught it before. That's something we've caught, but we're catching it with more detail tonight, which is really interesting. All right. Look at this overall shot. Is that not beautiful, guys?
It is.
Mm.
That's very nice.
Cosmic Ray says left side of the image should be blue. You got the real reds tonight. I don't know what you're seeing, Ray, but I've never seen the left side of the image being blue, even without the moon. This is all diffuse nebula in here. There's tiny reflection nebulae, but not vast tracts of blue reflection nebula in here. This is looking almost three-dimensional now. Holy cow. We're seeing this really intricate detail.
That is a very nice picture.
It's a great composition.
The full frame there, I mean, that's really something.
It is. In fact, I'm going to take us out a little bit more. Okay, there's the entire frame we're looking at right there. That's pretty. Let's just bring this up momentarily. Let's see where it wants to go with processing. Okay, not bad. And just darken it up a little more. Let's see where the color wants to go.
Dark nebulosity at upper left has a couple of really deep areas.
Yeah, it does. Okay, this is really close. This is really close to what it should look like. This is beautiful. Please go look at Ray's link that he put up, Daryl. The APOD. This is really nice. We're going to pull this down a little bit. Okay.
Ray, I strongly suspect that image you're referring to at the APOD
False
is
color?
it's a SHO.
Okay.
Hu-
False
Hubble
color,
palette.
Hubble palette. Yeah.
Yeah.
Not many things in the universe are going to be other colors than red, green, and blue. Blue reflection nebulae, oxygen 3, doubly ionized oxygen, and H2 or H alpha, which is the ionized hydrogen. Oxygen being the third most abundant element in the universe, stands for reason you're going to see a lot of it. What was that?
Oh, he put up another image.
Yeah. Okay. Look at this thing. Wow. Such detail as we've never seen before. Wow. Okay, let's bring back our stack and dock it to the bottom here. There we go. We've stacked 35 images. That's amazing for this region. It's incredible. Here we are. What a beautiful image. Holy cow. This is just beautiful. This looks so professional. I know. Silly, huh? Okay, let's bring the telescope back and look at it. Okay. There we go. Unbelievable. Good music for this too right now. My universe cathedral.
Looks like the dark nebulosity trails all the way across the top of the image now.
It does. Look at that. Disappears into here. Yeah, this is a superior image. Never ever seen it this beautiful before, ever. This is really quite phenomenal. And that's with the moon out too. Can you believe it? Holy cow! Look at that. Wow. Let's zoom out and let's see what else is in here. Let's pop this one. This is my artificial one that shows me everything that's in there. So you can see a rim around the whole thing like this, which I wanted to show you. That's the rim. And it's kind of visible when I do this. And we'll have to pull it out to show you.
That's amazing.
That's funny, Gladys. Michael Stargelo instead of Michelangelo. Creating his own cathedral. Oh yeah, this is the stellar cathedral that I just love sharing with all of you guys. You know, it is beautiful. It is really beautiful. We're gonna do this last exposure. We've been doing this is 40th exposure. Can you believe it? But we need that because we gotta wait for Measure 33 to come up above the building, and I think by the conclusion of this, it will. We've waited 23 minutes. Okay, so let's change the name here. This will be Elephants. This is the best Elephant's trunk ever, I'm telling you.
Mark,
wow.
Dugan wants to know what the camera model is.
Oh yeah, the camera model, James. And by the way, hi James. The camera model is the ZWO ASI. Okay, ZWO, that's all you need. ZWO 183 MC Pro. All right, it's a cooled camera. Right now we're running at minus 18.5 Celsius on the sensor, and that keeps the noise down. Very important on a moonlit night because we want to keep the stellar, or the noise rather, from the moon and so forth, lighting up the sky and causing incidental photons striking the sensor to be minimized, and this will help do that. Gosh, this is I don't want to leave this. This is just so pretty.
Yeah.
I'm gonna just drag this in a little bit. Yeah, look at that. Wow. I mean, it's looking three-dimensional. Let's see what the color correction will do. Oh yeah, the color correction, this is really a deep red in actuality, so this is correct. This is correct. Gladys says, definitely the most magical elephant trunk I've ever seen. Yeah, I guess you're right, Gladys. I guess you're right. Alright, let's drop this down so we can see the detail in here. That's really pretty. Okay, now we'll pump that back up and just approach our curve top to darken everything. There we go. Okay, one last save. Elephant's Trunk Nebula, or one, actually the save. We haven't done it yet. Alright. Save exactly as seen. So, when you go out and grab it on our server, this is what you're going to see. Okay, that's the image you'll see right there. Look at that. Yeah. Really pretty. Okay. Okay, Elephant's Trunk. Bye-bye. I'll be back. It's really so nice to do this again with the new camera because it just gives us the opportunity to see what we've been missing all this time. It's like I want to do the cave now and everything. You know? I mean, the cave is right nearby, but I want to do M33 as well. Before I do that, let's go see how high the Triangulum Galaxy is now. If it's above 43, then we're good. 45. Okay. We can see it now. And there we go. You'll see the moon down there. See it down there at the bottom? That's down at the northeastern horizon. There's Jupiter. Too low for us to see yet. Okay, this should be within view. I think we're just gonna miss the observatory building. Alright. So let's head north a little bit. Okay. All right. Let's give this a shot. Cosmic ray, I don't even know what that means. These images are mark images with marked crayons. Explain yourself. Okay, here it is right here. So we're going to go west a little bit. Yeah, if I have crayons that are, like $10,000 in value, yeah, I guess you're right. Yes, they're $10,000 crayons, right? Yeah. Okay. We're going to search now. That's good. All right, we're guiding, and we'll do a 35-second shot here. That's going to be actually pretty bright, but that's okay. All right. Good. And now we'll go back to our live stack. And before we clear it, let's look at that. Holy cow. Look at that beautiful Elephant's Trunk Nebula. Jeez. So dense, so much stuff going on in there. Truly looks like this is in the foreground, this is in the background. It may not be, but it just has that look. Hey there, Ronald is here with us, ERRT Radio. Okay, we'll clear this now and take our first image of measure 33. Are we clear of the building? Looks like we are. And yes, we are. So let's do that. Color correct. And do this. All right. All right, and now what we'll do is bring this over toward the peak just to darken things up a bit. Moon's definitely getting brighter, as you can see. But already, something else that's happening is really fascinating, is that we can see detail within this nebula right here. The detail within this nebula right here. That's why I said 35 seconds might even be too long. But if we do this, if we drop this down, then you can see some detail out there. Detail here, that's a supernova remnant right there, and it really is quite extensive in the image, and you can see the loop structure in this one over here, but you gotta let us zoom in. By the way, make sure you're at 1080p or this is gonna look kind of crappy to you. The best view is at 1080p. Let's add some contrast here.
Here I am stuck on Skype.
Well, Skype has given you the 1080p.
Okay.
So you're seeing it just fine. At least you should be.
Yeah.
Oh, Cosmic Ray is saying that the colors are assigned by me. No, they're not. At all. Actually, when I do a color balance, that's not me. When I say color balance here, okay, that's the color that the sensor is tuned for, and it's tuning the colors based on the frequency of light coming in, and it's translating that to a certain color. So, and there is a red, green, and blue component to that light coming in, and it represents it realistically. I'm not changing those colors. See, like this green here, I didn't assign that color, it did. This red, I didn't assign it, it did. So, you know, that's what's happening. Now, when the moon comes up, for some reason, the moon slants the color, and I have to drop the red by a tiny, like 0.8 or something, or 0.08, to get it correct. And this is a correction I'm making on the fly. So, yeah, in a sense, I'm doing that. But I have to, because this is a realistic view. So when I just let it color correct, when the moon's up, it does this. It makes it look like a red cast. It kind of fools it. So we have to drop it by a tiny fraction to do this. Look at that, though, huh? This is going to be just a gorgeous, gorgeous image. It will be as if there's no moon. Hey, what do you want? Gladys, this is Messier 33, which is a galaxy 2.7 million light years away in the constellation Triangulum. It's really something else. It's a gorgeous, gorgeous object. Right, and so you'll see that it's like a face-on galaxy. We're kind of looking at it like this. Okay.
Yeah, it's sometimes called the Pinwheel Galaxy.
Yeah, but I don't want to confuse that with the actual Pinwheel Galaxy that's known as the Pinwheel Galaxy either.
M101?
Yeah.
Oh, they call them both Pinwheel, don't they?
Yeah. But I assigned that Pinwheel to Messier 101 for my purposes. You may call it the Pinwheel. I just don't want to confuse folks. Oh, I thought, so is this the Pinwheel? Where's the supernova? You know, that kind of thing. And Messier 101's not even up right now to see. It's low on the horizon, actually. It might be up, but not to us. So let's do that. Alright, so if you look, you'll see, look at these loops up in here. Let's zoom in a little bit. It's still going to be just a little noisy, but I can drop the noise a little bit.
NGC 604.
604, you got it. Right, we'll drop this down. And now you'll see that there's structure in here. We couldn't see this structure before. Now we can, and it's really pretty. We couldn't see the structure of this supernova remnant. It was just a green blob. Now we see the structure. We couldn't see this spherical remnant around this area here for this supernova. But now we can. We couldn't see the detail within this nebula. This would be approximately the size. This guy would be like the Eta Carina Nebula in our galaxy. All right. And this might be something slightly smaller than the Eta Carina Nebula in our galaxy, as seen from here. And then down below here, we had another supernova remnant down here. Green one. Where'd it go? Oh, there it is, right here. Here's another one right there. And if we let it decide what it wants to do, it does that, right? So the moonlight causes it to overblow the blue background just a bit. So we gotta constantly bring this back. But that's fine. I do not mind that. Here we are. Okay. And let's do the color correction again. And modify a little. There you go. Let's turn off the enhancement. Okay. We can leave it. It's working okay. Because I added on just enough to show detail without blowing anything out. That's nice. I'm noticing that the moonlight is getting bright enough so that it's causing a blue halo around our object. So in processing, we'll try to remove that for you. Okay. This is the Triangulum Galaxy. We'll go to 15 on this one. Well, we go a little more. Okay. Hey, Donald Kunzer. Good to see you. I missed you. Alright, let me read here. Kunzer Gray says, then why are all the images from other images and people so different? Because they're using different palettes in order to process their images. As Daryl pointed out before, the SHO palette, the sulfur 2, hydrogen alpha, and oxygen 3 palette, where those colors are assigned of a specific set of coloration, that's the Hubble palette. But you know, you got to be careful when you look at images, because what you see ain't necessarily the actual color of the object anymore. People are very enamored with this Hubble palette. I guess maybe it shows more detail in the hydrogen alpha versus the oxygen 3, because they each show different things very clearly. Sulfur 2 as well is red, but it shows detail that hydrogen alpha complements. So there are things like that that are really interesting to see when we consider that aspect. Okay, that looks pretty good. Look at the detail, huh? This is really nice. All right, we're at 18 stacked here. Gladys says space is actually cold and soul-sucking. Well, actually, yeah, but let me tell you this about space, okay? You compare outer space with inner space, the deep ocean, and if you were exposed to the deep ocean for a fraction of a second, you're dead. But if you're exposed to the vacuum of space for a fraction of a second, you could live. You could survive that. And the reason is because it takes time for your blood to boil near the surface, and it takes time for the effects of zero pressure to affect you. But the effects of 6,000 pounds per square inch pressure, oh my, that's something that you can't endure even for a fraction of a second. It crushes everything on all sides, because the weight of the water column over your head plus the atmosphere above that all the way up to space is what you're feeling around you. down around Titanic. Well, that pressure approaches 7,000 pounds per square inch. Okay, and that's per square inch, 7,000 pounds. Okay, so we're talking about you know several tons per square inch. That's you can't handle that. Your body would not be able to handle that. No, you wouldn't get crushed flat into jelly. That's a myth, because water is incompressible, and most of your body is made of water. What gets crushed are your sinus cavities, your lungs, okay, and that's about it. The ear canals, and the inner ear, especially. But the brain is full of water, so your skull's not going to be crushed. But the thing is, you can't compress those things. You could, if you could breathe water, you could go to full ocean depth, all the way to the bottom of the deepest Challenger Deep, and be okay. It would just probably be something you'd have to get used to. Like when you saw in the abyss, there was a liquid breathing. Okay, that was a oxygen supersaturated solution. They said that you could breathe. Well, they didn't make that up. The Navy experimented with a liquid breathing apparatus, actually, and you did have a hard suit helmet, and it was filled with this highly saturated oxygen liquid pumped through your lungs. And they did experiment with it, and yes, divers could go thousands of feet down and not feel any relatively ill effects, right? And the thing is, they're looking through the solution in their masks, and so they had to get their eyes used to being able to do that. Number one. Number two, that liquid breathing process put liquid into the lungs, and you really have to make sure that you're filling the lungs completely, because if you don't, then you're going to end up having this massive collapse in one section of your lung, and that'll kill you. So it turned out that it wasn't practical, and they abandoned the program. But those that actually tried it ended up with bad pneumonia for months, because the pneumonia, the physical pneumonia, is liquid in the lungs, and it's this stuff has to get reabsorbed into the body, and it takes a long time. So it was very impractical. Yes. Well, Gladys, if you could somehow step out of a submersible down at depth, then yes, you'd be crushed. All the parts in your body that could be crushed would be crushed, and that's a very relatively instant death. But in space, with low pressure, zero pressure, you actually do have a better chance of survival during a vacuum than during this high pressure. They did a vacuum chamber experiment where one guy actually was exposed for a couple seconds to a vacuum. And it wasn't intentional, it was an accident. And he actually, he ended up surviving, but he was really in bad shape from it. But he survived. Had that been a deep ocean test and it was 6,000 pounds per square inch, he'd be dead. Okay. Triangulum Galaxy, we're going to save it like this. It's going to have a blue halo because of the moon. And that's not good, but I'll have to deal with it, I guess. Alright. Wow. Well, I think we got some really nice objects before the moon rose too far. And we'll do this again on another night. I saved our galaxy, so it's going to be up on the server. Again, you find the server at skytourlive.org. All right. So please enjoy. Feel free to head there. I'd love to have you there. And hopefully you can also visit our Etsy store. We'd love to have you at this store, and that's Sky Tour Shop on Etsy. And if you have questions for me, you can send them to MUFONanalyst@gmail.com. That's MUFONanalyst@gmail.com. All right. So you can send those to me directly, and that gets right to me. So, we are going to head out of here. It's been a long night. Check out our Etsy store at SkyTour Shop on Etsy at etsy.com. Check out skytourlive.org, where you can see these pictures, get photos, get really cool swag stuff if you want to, and hang out with us. I'm going to make contact with some of our other pages. Now look at that. See that? See what's happening now? It's moving around. We're ending just in time because the desert winds are kicking in. So that would have ruined all of our future shots. Excellent. We got just in time. Excellent. All right, guys. I hope you have a good evening. And from Daryl and I, we wish you the best. And remember, when you go outside, keep looking up. And we will talk to you another time.
Good night, everybody.
If not tomorrow, the night after. But we'll see. Once we get a spate of clear weather, we just go for it. So good night, everybody. Have a really good evening. And we'll leave you with this.